Hi, welcome back to the Tutor Wizard. I'm Adrian. Please subscribe right here. You'll get notifications for this series and a bunch of other ones on our channel. What we're doing is video 5 in multivariable calculus. We're in chapter 1, partial derivatives. We're doing section 1.2 now, which is limits and continuity, and this will be the first video in section 1.2, limits and continuity. This lecture, what are we going to do? We're going to do limits of functions of two variables, x and y, and some examples. All right, starting off with limits of functions of two variables. We're going to start, before we give the definition of a limit of a function of two variables as we approach a value a, b in the plane now, we're going to consider two examples that both approach 0, 0. One of them is going to exist, it turns out, one of them is not going to exist, and so we're going to look at the behavior and and then I'll draw the graph of these two functions of two variables in a second. But for now, if I look at the same way we would when we're looking at limits of a function of one variable, we're trying to say that the y values get arbitrarily close to L as x gets arbitrarily close to A. Now we're doing it in two dimensions, so we're trying to say that xy is going to get arbitrarily close to 0, 0. And then we want to see what happens to our function z, which is f of xy. What do they approach? What is this table telling us? This table is telling us that for x and y values, I'm putting those xy values into our function z equals f of xy, and then we're computing those values. So that's what the table has in here, basically. Once we have, I've just picked a bunch of x values and a bunch of y values, then I'm putting them into the function and computing their values. So then again, I have a bunch of x values and a bunch of y values. And I picked a bunch of values near 0, getting closer and closer to 0 to see what happens. In this function, it looks like I'm getting closer and closer to the value 1 as I get closer and closer to 0, 0. And in this one, it seems like I'm not really approaching any value. This way I'm approaching 1, and this value I'm approaching -1. And so that doesn't seem like I'm approaching any value as I get closer and closer to 0, 0. Okay. These are what the surfaces look like. So now you can see this one's sort of a hot mess at 0. I tried to draw it the best I can. Obviously, you can use the internet and use Desmos or some kind of GeoGebra to 3D draw these, and they will look better than what I drew here slightly, but the computer will generate these for us as well. But for now, this is what the sine x plus y over x plus y looks like, and near 1 it looks like it is 1, or near 0, 0 it is 1. And here it looks like it doesn't exist. It's approaching these hyperbolic type things, and it's doing weird things near 0, so it's not going to exist. What we'll do is now give the definition of what limit is near a value a, b in the plane, and then do some more examples beyond this. All right, for the specific rigorous definition of what limit of a function of two variables is as xy approaches a, b, we say that let f of b a function from d to r, and let a be a point in D. We say that the limit of f of xy as xy approaches ab is the limit L, and we write the same limit as we did before, except we have two variables now, equals L, if and only if, by definition, and now if you haven't seen this before, quickly here, I'll put this over here, for every is for all is what that means, upside down A, and backwards E is there exists. This is the universal and existential quantifiers for predicate logic. But for now, all you need to know is upside down A is for all, and backwards E is there exists. Okay, good. Okay, one more time. The limit as xy approaches ab of f of xy equals L if and only if for every epsilon greater than 0 that we have, there exists a delta greater than 0, such that for every x, y, and d, if the distance between, this is saying distance, if the distance between x and a, x, y, and ab is less than delta, then the absolute value of f of xy minus L is less than epsilon. What is this algebraic hot mess really saying to us? Let's draw a couple pictures and then we'll remind ourselves underneath what this definition is again, and we'll try to see what pictorially what this algebraic thing is trying to say about when we have a limit. All right, pictorially, what we've got is what the limit is saying is, if we look at the domain, first of all, what it was saying was in that horrible for every epsilon business, what that's saying is we have to have, if the distance between the point xy in the plane is between the distance between xy and AB is less than delta, that means that they're inside this disk of radius delta. We're going to call that d delta for obvious reasons. And so if we have a point which is inside that disk, what it's saying is then the value of f at xy has to be inside this interval. It has to be within an epsilon radius of, in one dimension, of L, our limit. And that's what we're going to say is the limit is of f of xy is L. If we can have that the distance between xy is less than, between xy and AB is less than delta, and then the distance between f of xy in one dimension and L is less than epsilon. That's what our limit is saying. And then again, with a fancier picture, and this is an alternate notation of saying what these pictorially are representing. The values of f of xy can get arbitrarily close to L as xy is made arbitrarily close to but not equal to the point AB. This is limits of functions of two variables xy. Good. Okay, the last thing we need to strategize before we do a couple examples is a really good way of telling when a limit doesn't exist when we approach a value. We notice that if the limit of f of xy is L, then it must be this value no matter how we approach AB in the plane. See, in the plane, if we have even a region, we may be able to, if this is the coordinate axes, we may be able to approach, if this is AB, we may be able to, and then we have this, we might be able to approach xy with a straight line or this curve or all kinds, but what it's saying is regardless of how we approach AB from xy, we must have that this limit is going to be the same value L. Using the contrapositive of this, so if the limit exists, then all paths go to the same value L. Using the contrapositive, if we can find at least two paths that have different values as they approach AB, then the limit does not exist. And that's exactly what our theorem says. Our theorem says if f of xy is a function of two variables and it approaches L1 as xy approaches AB along a curve gamma 1, and if f of xy approaches some other value L2 where L1 is definitely not equal to L2, two distinct values, as it approaches another curve gamma 2, then this limit does not exist. And so a good strategy for doing this is, if you suspect and you start computing and you can't see how to use this horrible epsilon delta definition, quite often we're going to give you ones that don't exist, and a good argument is to try to cleverly look and find two paths where I get different values for the limit and therefore it doesn't exist overall. I won't do it here, but to speed up the process, or the thought process of what we have to do is I would do the same thing as we did at the beginning of the video. I would compute a table of values and I would try to see where it's approaching, and it would seem like it's not approaching a particular value in this case, and so that may even give you insight into which two different lines you should use to show that this limit doesn't exist. So after computing a bunch of values, blah 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 blah, I suspect that this limit doesn't exist, and how am I going to show that it doesn't exist? I'm going to use the theorem we just stated, which says I'm going to try to find two paths that approach 0 and I get a different value in my limit. So curve 1 along the x-axis, say, which means y is 0. If I approach 0, 0 along the x-axis, what that's saying is my function f of xy in this case would equal x times 0 over x squared plus 0 squared, which is 0 over x squared, which is 0. along this curve, which means that the limit as xy approaches 0, 0 of f of xy is going to be 0 along the x-axis. Now, if I cleverly look at, and in the table you might notice that it might approach a non-zero value along the curve 2, which is the line y equals x in the plane. So curve 2 along the line y equals x. Along this, what do I get? I see that f of xy is going to equal x equals y. So let's replace y with x. So that gives me x squared over x squared plus x squared, which is x squared over 2x squared, which is cancel, 1/2. So that says that the limit as xy approaches 0, 0 of f of xy is equal to 1/2 of f of xy is equal to 1/2 along curve 2. What that says is I've got a limit L1 and then a limit L2, and 1/2 doesn't equal 0. And what that says is, by the theorem, this says that the limit as xy approaches 0, 0 of f of our function, which was xy, x squared plus y squared, does not exist. Next example. All right, example 2, compute the limit as xy approaches 0, 0 now of a slightly different function, 2xy squared over x squared plus y squared, or state why it doesn't exist. All right, first of all, if I try to play the same game, if I look at along the x-axis, this is when y equals 0. This is going to give me f of xy is 0 again, which says the limit is 0 along the x-axis. Along the y-axis, if I try another path, that's when x is 0. That's also going to give me f of xy is identically 0 along this path, which says that the limit is going to be 0 in this case. So regardless of what we get, if the limit exists, it has to be 0. Otherwise, we've got at least two paths where we're computing 0, and we couldn't have something different than that. We've checked at least one path, and we have that a limit of 0 along one of these paths, so it should be 0 along all these paths, or the limit doesn't exist. What does this mean? Therefore, if the limit exists, we suspect it must be the limit L equals 0. Now what do we have to do? We have to run the definition of showing that rigorously. What does that mean? We need, for every epsilon greater than 0, we need the fact that there exists a delta greater than 0, such that for every xy in our domain D, which will be R2, remove 0. What we're going to look at is, what do we need? If the distance between xy and 0, 0, so x squared plus y squared, if that's less than delta, we need that f of xy, the absolute value of 2xy squared over x squared plus y squared minus 0 has to be less than epsilon. That is our technical definition of a limit. Now, how are we going to find that? Now, if you've never done this before, we're not going to do it too much in this class. We're just going to delve, and I'm going to do at least one example. Delta is actually a function of epsilon, and what we have to do is sort of fudge this and calculate this and try and make this inequality look similar to this inequality in some clever way, and then we can cook up a delta which depends on epsilon, and the limit will be 0. Let's do that. 2xy squared over x squared plus y squared has to be less than epsilon. But that is if and only if 2 absolute value x, y squared, x squared plus y squared is less than epsilon. Now what we're going to note is, from this I can see that y squared is less than or equal to x squared plus y squared. And this means if I reciprocate 1 over that, 1 over x squared plus y squared is less than or equal to 1 over y squared. Now I build this. What that says is, or from this, what you can do is multiply both sides by y squared, which is positive, which won't change the inequality. And that says y squared, x squared plus y squared is less than or equal to 1. And so when I'm building this, I want to multiply both sides by 2 absolute value x. This says that the absolute value of 2xy squared over x squared plus y squared minus 0, our limit, which it disappears in this case, has to be, if I multiply 2 absolute value x on both sides, 2 absolute value is the 1, 2 absolute value x, then you can see that I get this is less than or equal to 2 absolute value x. I know, you can rewind and see what I'm doing here. Basically, I'm using inequalities to cook up this expression, and I want to find it where it's less than delta, or less than this. So I want to now compare it to this somehow, so I can cook up a delta. What I noticed cleverly is this is 2 to the square root of x squared, and that has to be less than or equal to 2 times the square root of x squared plus y squared, because if I add a positive or non-zero quantity, it can only get bigger. And that's exactly this, which would be less than delta. Therefore, what do I need? That would be less than delta if when I'm going to let delta equal epsilon over 2. And that will give us exactly what, or sorry, I want this to be less than epsilon. It's my function. What does that tell me overall? It takes time to learn how to cook up this delta from the epsilon. But we have now, specifically using our definition, this is what we were looking for. And now what do we have? If we cook up this delta equals epsilon over 2, we have exactly what we need. This says, just using the definition, we now have, for every epsilon greater than 0, there exists a delta, which is epsilon over 2, such that for every xy in the domain D, we have if 0 is less than the square root of x squared plus y squared is less than delta, then this says our function, which was 2 absolute value, or x squared, xy squared, x squared plus y squared minus 0, is now less than or equal to what? 2 square root x squared plus y squared, which is strictly less than, this is less than delta, 2 times delta, which is equal to, now what was delta? We picked it to be epsilon over 2, which is now the 2's cancel and gives us epsilon. What that really says is, if you want to write it out one more time really nicely, that says by definition, for every epsilon greater than 0, there exists a delta which is equal to epsilon over 2, such that for every xy in the domain D, if the distance between x, y, and 0, 0 is less than delta, this says that 2xy squared over x squared plus y squared minus 0 is less than epsilon. Please hit the notification or hit the bell to get notifications for this series and many others. We'll see you next time.